Hey there everyone, welcome to Software's classes. In front of you is a question about the autoregressive scheme, that is autocorrelation, right? So the first part of this question is, consider the first order autoregressive scheme in the general regression model. So how would you estimate the variance, covariance and autocorrelation coefficient of the disturbance term of the model? In order to answer this question, let us first start with what is autocorrelation, right? So the first thing first, that is autocorrelation. So what is autocorrelation? Now we know that there are certain assumptions of a random variable under a CLRM model, right? So when we violate the assumptions of CLRM, we have few problems, and one of such problems is autocorrelation, okay? So autocorrelation is a special type of correlation. So which assumption of CLRM is violated that suggests autocorrelation? That is assumption 4 of CLRM. What is the assumption 4 of CLRM? That is the simple linear regression model. It says that your covariance of UI uj, that is covariance of two disturbance terms, is equals to E of UI uj is equals to 0. That means error terms are independent of each other. The disturbance term of two different periods are independent of each other. They are not related, and that is our assumption of CLRM. Now when this assumption is violated, we have problem of autocorrelation. We have the problem of autocorrelation. So now what is then autocorrelation? So autocorrelation is E of UI uj is equals to, which is our cov of UI uj, not equals to 0. That is the meaning of autocorrelation, which means disturbance terms of successive time periods are related. Okay, they are related or are dependent, and that is our problem of autocorrelation, and that is what we mean by autocorrelation. Okay, so that means, let us write down a model. Let us write down a simple linear regression equation with autocorrelation. Okay, so when I'm writing down the equation, it will look like any other simple linear regression, that is yi is equals to alpha plus beta xi plus ui. Okay, now since there is this problem of autocorrelation, so I can say that this ui, that is here E of UI uj, is no longer equals to 0, so it will not follow CLRM. Okay, now mostly the problem of autocorrelation occurs in time series data. Okay, that is, our regression line can be written as yt is equals to alpha plus beta xt plus ut, where t is equals to 1 to infinity. Okay, now let us try to relate the disturbance term with its preceding disturbance term. As we know that here there is problem of autocorrelation, that means the disturbance terms are related. So let us write down a linear relation between the two successive error terms. That is, let ut is equals to rho of ut minus 1 plus epsilon t. Okay, so this is disturbance term of period t. This is autocorrelation coefficient. autocorrelation coefficient. This is the disturbance term of t minus 1 period, that is the period preceding the disturbance term that we are taking here, considering here, and this is our any random error while taking this relation, okay, and it follows all property of a random variable, like that is expectation of a random variable, which is your epsilon, right, is equals to 0, of square is equals to sigma epsilon square, so that our variance is constant, and epsilon I epsilon j is equals to 0. So these properties are satisfied for this random error of the disturbance terms who are related, that is they have the problem of autocorrelation. Now let us see one more thing. So since we know that the present period error term is autocorrelated with the error with the disturbance term of the preceding period, so likewise we can write down the following equations, that is for period t, if ut is equals to rho ut minus 1 plus epsilon t, then for period t minus 1, rho is rho times ut minus 2 plus epsilon t minus 1. Again, t minus 2 will be rho ut minus 3 plus epsilon t minus 2, and so on till say a time period r. So that will be ut minus r plus 1 plus epsilon t minus r. So this is the sequence of our relation of disturbance term with the previous period's disturbance term, and this shows the problem of autocorrelation. Now we can form a sequential or serial correlation equation by substituting the values in every equation starting from 1. Okay, let's say this is 1, this is 2, this is 3, this is so on and 4. Okay, so what we're going to do, let us put 2 in 1. So what do we get? We get ut is equals to rho in ut minus 1. What am I going to put? I'm going to write down this u. So in this ut minus 1, I'm going to write down this, that is rho again ut minus 2 plus epsilon t minus 1, and I already have epsilon t, correct? So now we can put the value of ut minus 2 here similarly, that is equals to rho square rho ut minus 3 plus epsilon t minus 2 plus rho epsilon t minus 1 plus epsilon t. Again, in place of ut minus 3, we can write down rho square into rho. Okay, first let us simplify it, then we will substitute the values. So that is, after simplifying, we get rho cube ut minus 3 plus rho square epsilon t minus 2 plus rho epsilon t minus 1 plus epsilon t. Now again, in place of ut minus 3, we can write down rho cube rho ut minus 4 plus epsilon t minus 3 plus epsilon t minus 2 plus rho epsilon t minus 1 plus epsilon t, and we can go on like this, right? So ultimately what we will get is ut is equals to, if I simplify this, then we can write down it as epsilon t plus rho epsilon t minus 1 plus epsilon square epsilon t minus 2 plus epsilon plus rho cube epsilon t minus 3 plus rho to the power 4 epsilon t minus 4, and so on. So in general, we can write down ut is equals to summation of r is equals to 0 to infinity rho to the power r epsilon t minus r. That is, if we put the value of r is equals to 0, we get the first term epsilon t. if we put r is equals to 1, we get the second term, rho into epsilon t minus 1, and so on. So this is our relation of the disturbance term when it is autocorrelated, also called the first order autoregressive scheme. So now what we're going to do is calculate the mean of this first order autoregressive equation, right? So mean of ut, that is E of ut is equals to E of summation r of rho to the power r epsilon t minus r, which is equals to rho to the power r summation r expectation of epsilon t minus r. Now we know from the assumption that expectation of this random error is equals to 0. Therefore, epsilon, the expectation of ut is equals to rho to the power into 0, which is equals to 0. That means mean of the disturbance term when it is autocorrelated is 0. So E of ut is equals to 0. So this is the mean. Now next one is we are heading towards to calculate the variance of ut when it is autocorrelated. So variance. So for that we will need what? We will need E of, so basically variance of ut is equals to expectation of ut minus E of ut whole square. Now we know that this is 0, just now we have proved, so we can write down what? That variance of ut is equals to expectation of ut squared, right? Now in place of ut, what am I going to write? I'm going to write variance of ut is equals to expectation of summation rho to the power r epsilon t minus r squared. Now what we are going to do is, now this is equals to summation rho to r expectation of epsilon t minus r squared. Now this again from the assumption of the random variables and hence the random error, that this is nothing but sigma square epsilon, right? That is the variance of the epsilon term. So here we have got variance of ut is equals to summation rho to the power 2r sigma square epsilon. Now what is this r is equals to from 0 to infinity? Let us expand this. So we get sigma epsilon square into, inside we have, when it is 0, so we have 1 plus rho square plus rho to the power 4 plus rho to the power 6 plus dot 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 till infinity. Now this expansion is a GP series expansion, and from that what we can write down? We can write down this expansion as, this is what we have got by 1 minus rho square. So this is the expansion of 1 minus rho square. Therefore the variance of the disturbance term when it is correlated is equals to sigma epsilon square by 1 minus rho square, and that is the answer. That means mean is 0 and variance will be this particular value when the disturbance term are correlated with the successive disturbance term of the time period, right? Now next we have to find out the correlation between the disturbance term of the successive time period. So for that, let us have a look. So for that we have ut is equals to epsilon t plus rho square epsilon t minus 1. Just a moment. Sorry. This is rho, right? Yes. epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus rho cube epsilon t minus 3 plus dot dot dot. Similarly, ut minus 1 is equals to epsilon t minus 1 plus rho epsilon t minus 2 plus rho square epsilon t minus 3 plus dot dot dot. Now, covariance of ut comma ut minus 1, that is equals to, what is the formula of covariance? E of ut minus expectation of ut times ut minus 1 minus expectation of ut minus 1. So now we know that the mean of these disturbance terms, even when they are autocorrelated, is 0. So since E of ut is equals to 0 and E of ut minus 1 is equals to 0, therefore covariance of ut minus 1 is equals to expectation of, I can say, ut into ut minus 1, right? Now, in place of ut and ut minus 1, we can write down the expanded formula, right? That is E of, what is ut? Ut is epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus rho cube epsilon t minus 3 plus dot 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 into epsilon t minus 1 plus rho epsilon t minus 2 plus rho square epsilon t minus 3 plus dot dot dot. Now, let us take this as epsilon t plus, let us take rho as common. So we have inside the bracket epsilon t minus 1 plus rho epsilon t minus 2 plus rho square epsilon t minus 3 plus dot 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 into epsilon t minus 1 plus rho epsilon t minus 2 plus rho square epsilon t minus 3 plus dot dot dot. So now here let us multiply, right? After multiplication, what we have? Epsilon t into this, that is epsilon t into epsilon t minus 1 plus rho epsilon t minus 2 plus rho square epsilon t minus 3 plus dot 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 plus, now we have this is rho into epsilon t minus 1 plus rho epsilon t minus 2 plus rho square epsilon t minus 3 plus dot 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 whole square, because see, this and this, they are same, so we are multiplying, so this is square. Now let us apply expectation. So if we take expectation of et, so we know that expectation of this is equals to 0. So this term is basically 0 and we are left with, so covariance of ut minus 1 is equals to rho expectation of epsilon t minus 1 plus rho epsilon t minus 2 plus rho square epsilon t minus 3 plus dot 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 whole square, right? Now let us take the square values, that is rho into we have e here, so this is epsilon t minus 1 square plus rho square epsilon t minus 2 square plus rho to the power 4 epsilon t minus 3 square plus dot 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 plus, now we have the cross products, that is 2 into epsilon t minus 1 into rho of epsilon t minus 2 plus again 2 into epsilon t minus 1 into rho into epsilon t minus 3 plus dot 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 dot. So now if we take the expectations here, so we get is equals to rho of expectation epsilon t minus 1 square plus expectation epsilon t minus 2 square and we have the rho square of course here, and so on, plus the cross products will be 0, right? So what do we have here? We have rho expectation of epsilon t minus 1 square, and inside we have 1 plus rho square plus rho 4 plus dot dot dot. Now this is again nothing but this, all the values, these are all, so I've taken the common as 1, so this is nothing but our sigma square of epsilon. So we can write down rho into sigma square of epsilon times, this is the GP series expansion, that is 1 by 1 minus rho square. So here after calculation what we have finally got is covariance of ut and ut minus 1 when they are correlated is equals to rho sigma epsilon square by 1 minus rho square. Now this term, if we recall, is nothing but the variance of the random disturbance when it is autocorrelated. So this is rho into sigma u square basically. Okay, this is the value which is not equals to 0, of course. So they are autocorrelated, and this is the value of the correlation of autoregressive scheme of order 1. Now that we have got it, so, and we also have got the mean value, we will just see whether when this UT are autocorrelated, they will yield unbiased estimator or not. So what is the unbiased estimator of this disturbance term? That is the next thing that we are going to calculate. Now from this simple linear model, so we know that the value of beta, that is the parameter beta from OLS estimate, is beta hat is equals to summation xi yi by summation xi square. Okay, now this small xi is the deviation, that is x minus x bar, and small y is equals to y I minus y bar. Now since the linear regression equation is what, yi is equals to alpha plus beta xi plus ui, right? Now if we take the mean value, then we get alpha y bar y bar is equals to alpha plus beta x bar plus u bar, and of course this u bar is equals to 0. Now if we subtract these two, what do we get? If we subtract these two, so yi minus y bar is equals to alpha gets cancelled, 0 plus beta into xi minus x bar plus ui. Now this is small yi is equals to beta into small xi plus ui. So from here I can write down what, that yi is equals to beta xi plus ui. So I'm going to put this value in the yi value, that is, since beta hat is equals to summation small xi yi by summation xi square, so in place of yi I will write down this value, right, that is beta xi plus ui by summation xi square. So now here what we have got is beta hat is equals to beta summation xi square by summation xi square plus summation xi ui by summation xi square. So this gets cancelled, so we have beta hat is equals to beta plus summation xi ui by summation xi square. Now in order to find out the unbiasedness, we have to take the mean, that is expectation of beta hat is equals to expectation of beta plus summation xi expectation of ui by summation xi square. Now we know that the expected value, that is mean of the disturbance term ui when it is autocorrelated, is 0. So since E of ui is equals to 0, we have, and this beta, it is constant, so this is beta, so we have E of beta hat is equals to beta plus 0. So E of beta hat is equals to beta. That means, therefore, it is beta hat is an unbiased estimator. Even when U is autocorrelated. So that's it for our autoregression derivations.